The paper we're diving into today is Low-Cost Experiment to the Correct Relativistic Energy Formula by David Lush. Bit of a mouthful, but honestly, the questions it raises are pretty fascinating.
Yeah, this one really made me sit up. Basically, Lush asks, hey, what if the formula we all use for relativistic energy, Einstein's famous E equals mc squared thing, isn't actually the most fundamental version? Like, what if there's another valid formula that works just as well, or maybe better in certain contexts?
Right. And in this paper, Lush compares Einstein's version with an alternative that's been proposed by OSIAC. So the big question he's trying to settle is, which relativistic energy equation actually reflects physical reality? I mean, no big deal. Just trying to overturn 100 years of physics.
Yeah, small potatoes. But seriously, the significance here is huge, right? This basically gets right to the foundation of modern physics. If our main energy equation is off, even slightly, it might ripple out into how we understand everything from particle physics to cosmology. Stuff like dark energy, inflation, even dark matter.
Exactly. The alternative formula comes from OSIAC's idea, which is built not from Einstein's 3D Planck equation, but from integrating the Minkowski equation. The four-dimensional approach. And OSIAC's version actually gives a rest energy that's half of Einstein's. So instead of E0 mc squared, you get E0 equals mc squared over 2.
Yeah, and for moving particles, the formula is even more wild. It becomes E equals gamma squared mc squared over 2. So it's quadratic in the Lorentz factor gamma, not linear like the standard E equals gamma mc squared.
Here's a quirky thing, though. OSIAC's formula lets gamma, the Lorentz factor, be negative, without invoking any of those weird negative energy states that give physicists nightmares. That opens up whole new interpretations for antimatter and time symmetry.
Which is kind of trippy. But Lush points out there's a downside to OSIAC's approach. It doesn't conserve energy in relativistic particle collisions. Apparently, that's the main reason Einstein's version became standard. It's the only one that keeps energy conserved when things are moving really fast.
True, but Lush argues that energy non-conservation might actually be a feature, not a bug. He ties it into all these weird cosmological observations, like why the universe is expanding faster than expected, or why dark energy might exist at all.
I liked how the paper keeps circling back to experiments. Lush proposes a clever, low-cost experiment using standard pair creation, shooting gamma rays at heavy nuclei to create electron-positron pairs. The idea is to check if the positron literally appears after the event, as standard theory predicts, or if it could be detected before, according to OSIAC's framework.
The thing that jumped out at me, if OSIAC's right, positrons, which are like time-reversed electrons, might actually be detectable before they're created in the lab frame. That's wild. Like actually probing the nature of time with a particle detector.
Yeah, it starts getting into that realm where physics feels more like science fiction. But Lush provides practical tests. Look for time advances in positron detection. Compare trajectories in magnetic fields. Actual empirical ways to distinguish between theories.
And he brings up this whole thing about how changing the energy formula might explain the missing mass in galactic rotation curves, classic dark matter problem, without needing some new particle. If you double the energy in certain collisions, you might account for that extra gravity.
Right, though, I have to admit, there's a part of me that gets suspicious here. Like, physics is full of people dreaming up alternative models that try to explain away dark matter or dark energy.
Yeah, totally. And honestly, not all of them hold up when the data comes in. But I think Lush's point is less about saying Einstein is wrong, and more that science should keep pushing at the boundaries and not rule out alternatives just because they don't fit the current narrative.
There's also this side digression in the paper about preons, remember? Like, what if quarks and leptons are made of even smaller bits? It doesn't totally flow with the energy experiments, but I guess it's all part of asking, What's really fundamental?
Yeah, I kind of lost the thread there for a minute. But the upshot of the whole paper is, let's not treat equations as gospel. Physics progresses when we're open to experiments that could shake the bedrock. I mean, we might not end up upending E equals mc squared, but even asking the question can tell us a lot.
Couldn't agree more. Even if this alternative formula doesn't pan out, trying to prove, or disprove, it pushes the precision of what we know.
The paper we're diving into today is The Magnetic Force as a Kinematical Consequence of the Thomas Precession by David C. Lush. Quite a mouthful, right?
Yeah, I had to read that title a couple times before it started making sense to me. But it's actually asking a really big question. Could the magnetic force, like the same kind of force we see in everyday magnets, just be a kind of side effect from the weird way space and time behave when things move really fast? Especially when you bring in something called the Thomas precession.
Exactly. And just for anyone who maybe hasn't thought about Thomas precession since physics class, or, ever, it's this rotational effect you get when a particle moves and accelerates at relativistic speeds, meaning near the speed of light. Basically, it makes the reference frames of moving particles rotate relative to each other.
And that's super fundamental. Lush's core argument is, what if the magnetic force, instead of being just one piece of Maxwell's equations, a kind of force on its own, is what you'd expect to pop up just from this kinematic twisting, this Thomas precession, as you switch reference frames?
Right. The significance here, and why I think it's actually pretty bold, is that it tries to demystify magnetism even further. Instead of electric and magnetic fields are two sides of the same coin, which is standard relativity, it goes, hey, maybe the magnetic force is what you have to see if you're tracking with all the correct frame rotations as charges get pushed around. It's like he's saying magnetism isn't its own thing. It's just the price of doing kinematics correctly in relativity.
Uh-huh. So to unpack the main method a bit, Lush considers two classical charged particles, one acting as a source and not accelerating, like it's super heavy or maybe it's part of a wire so it can't move. The other's getting flung around by the electric field, the Coulomb force. He's walking through like, what does the observer who rides along with this test particle see? From her perspective, reference frames are precessing, twisting around, all because of the Thomas effect.
And what's wild is that when you tally up all the pseudo-forces she expects, Coriolis, centrifugal, Euler, like the kinds you get on a spinning merry-go-round, some are there, some aren't. Specifically, there's no Coriolis force in the source particle's rest frame, because from that particle's point of view, nothing's turning. This means, though, that an anti-Coriolis force has to be popping up somewhere, almost as compensation. And that's what, in the usual inertial frame, looks exactly like the magnetic force. Seriously, that connection feels so satisfying. Like, you almost want to high-five relativity.
I know! And it's not just a formal analogy. In his equations, the magnetic force in the lab frame is identical to this missing or anti-Coriolis force viewed from that precessing test particle frame. You can see the math. He even gets the mass dependence to drop out, just like the real magnetic force, which only cares about the velocity and the charges.
And, he doesn't stop there. He teases out, okay, if the Coriolis term gives you magnetism, what about centrifugal and Euler terms? Could they hint at the origins of the strong and weak nuclear forces? I mean, that's a hefty leap, but his argument is that at really high energies, like inside an atomic nucleus, there might be a Thomas precession-induced anti-centrifugal force that could be, well, strong and always attractive. He goes as far as to do some quick calculations, comparing how it might stack up to the size of a nucleon. Spoiler, it's a bit too weak, but not wildly off.
He does admit that this isn't the last word, like it's just a start. There are things he hasn't calculated, like the effects of field retardation, so it's not perfect. But, the idea that maybe the deep forces of nature and all the fields we've cooked up, to Lush, maybe they're just labels we slap on the weirdness of special relativity plus classical kinematics when you're really strict about it.
There's something almost philosophical there, right? Like, is a force always a force? Or sometimes just the universe's way of bookkeeping as things zoom around with Einstein's rules?
For sure. And sometimes I wonder, like, if you could go back and tell Faraday or Maxwell, hey, what you thought was a core force of nature might just be a perspective effect if you're riding along with the particles, would they be delighted or horrified?
Ha!